you may recall that after vector addition and scalar multiplication were defined, the notion of linear combination was introduced. So if we have k vectors, u1 up to u sub k in Rn, and if we have another vector v, also in Rn, right, so we say that v is a linear combination of those vectors. Well, so I should specify this of u1 up to u sub k if there exist some scalars, if there exist scalars c1 up to c sub k. So these are real numbers. We use the letter c for coefficient. Okay, so if there exist such real numbers such that we can write v as the first scalar times the vector u1 plus the second scalar times the second vector all the way to the last vector, like this. Okay, so if for instance we take v could be equal to the vector, let's say 4, -1 in R2. Okay, and then one can check that 4, -1 is equal to times the vector 3, 1 minus 4 times the vector 2, -3 plus 3 times the vector 2, -5. Right, so in this specific example, well, n is just 2. These are just vectors in R2. K is equal to 3. We've got 3 vectors. Okay, so this is u1, this is u2, this is u3, and the first vector, 4, -1, this is v. Okay, so, all right. Here I'm using column vectors because, well, for most of this course we will actually be using column vectors, so one can easily go from a column vector to a row vector and vice versa. Right? If you have a row vector, you can just write it as a column vector like this. Okay, and do the same thing from column to rows. So this should not create any difficulty. There is a reason why we prefer column vectors to row vectors, and you will see it after you learn about matrix multiplication. So, all right, so we have this, this notion of linear combination, which is central in linear algebra. And what we can do is that we can look at all those linear combinations at once. And we get what is called the span of a set of vectors. So what I want to do in this video is to illustrate what is the span for small values of n and small values of k. And I'll show you some animation. But first, let me just write down the algebraic definition of span. So if we have vectors again like this, u1 up to u sub k in Rn, so the span of those vectors, so I'll move this up here, so the span of these vectors, u1 up to u sub k, this is the set of all linear combinations of those vectors. So of u1 up to u sub k. So if k is 1, right, a linear combination of just u1 is just a scalar multiple of u1. And if we look at the set of all scalar multiples of u1, what we get is a line going through the origin, 0, and having u1 as a direction vector. So this notion of span, well, is also central in linear algebra. So for mathematician with experience, this is a good definition. But you may ask, okay, I can try to conceive that, yeah, you can choose scalars, you can get linear combinations, you get a bunch of all new vectors, but what does this look like? Right? That would be a good question. Well, what is true is that if we look in R2, take the span of some vectors, well, you either get the line, if the vectors are already on the line, they are all parallel, or you get all of R2. If you look in R3, and you take the span of some vectors, well, if they are all parallel, again, you just get a line. If the vectors are not parallel, the span will be either a two-dimensional plane going through the origin, having two of those vectors as direction vectors, or the span will be all of R3. So this notion of span, actually, it generalizes to higher dimensions, so to Rn for n bigger than 3, these notions of lines and planes in R3 that we have learned about. So lines and planes in R3, we can picture them in our head in higher dimensions, right? So it's not possible. We cannot conceive of things in R4 from a geometric point of view. But inside R4, there are some subsets that kind of looks like planes. Sometimes they're also called hyperplanes. Okay, and we cannot visualize them, but we can study them using algebra. Okay, and we obtain them by looking at the span of a set of vectors, by looking at all linear combinations. Okay, so let me just show you so what these spans look like for small values of n and k, because I've got some animation to show you. So the first one, so we just take a vector u, so that's the vector 3, 1, right? So it's indicated up there. The vector w is the vector, it will be a scalar multiple of u. So this is the case here when k is 1 and n is 2. Okay, so you look at all multiples of the vector u. Okay, well, of course, I cannot look, on my finite tablet, I cannot draw all of them. Okay, but I can look at all the multiples, a times u, when a is between -3 and 3. Okay, and we can see what happens if I play this little animation. So a has value 1 for the moment, so w is equal to u. Okay, but if I start, if a changes values, now it's almost -3, then we'll go back up to 3. Okay, then you can see that all these scalar multiples of u, indeed they are all on the line going to the origin and parallel to u. Okay, so okay, so this you know already. This is the simplest case. Okay, so a line, the span of u is just a line. Okay, so and here you see some of the vectors on that line. All right, so let's look at something a bit more interesting. So let's say we look in the plane. So here maybe I want to zoom out a little bit. Okay, so I have u again. This time u is red. I've got a v in blue up here, and w is a linear combination of u and v. So it's equal to a times u plus b times v. So w is in yellow. Okay, and I can do something similar. So I can give a and b values between -3 and 3. Okay, for each just of values for a and b, I get one linear combination of u and v. Okay, then we can try to see what these all look like. Okay, so again, we cannot look at all of them, right? Because the tablet is finite, so I cannot give a and b all real possible values, but I can give them all values between -3 and 3. Right, so I can start giving them some values like this. Okay, and you see that, well, w will move around the plane. Okay, so in various directions. So it seems to be kind of going around the origin, stretching, shrinking, etc. Right, and well, based on this, you can imagine that since W can go into any direction around the origin, right? So if you increase A and B enough, you'll be able to obtain all the vectors in R2. And this is indeed the case, that because U and V are not parallel, their span will be all of R2. Okay, so, and this, well, I think this is believable just based on this little animation. This can be also checked using algebra. So one can show that for these U and these V, any vector in R2 can be written as a linear combination of U and V. This can be done by solving a system of equations. Okay, and you'll see some examples. All right, so what if we go to R3? So, all right. So here the axes are maybe a bit confusing. The z-axis is vertical, it's blue. The x-axis is actually the red axis here. And the y-axis is that sort of green axis going in that direction. Okay. Going kind of further away from you. So I've got, again, two vectors, U and V. U is in red, the vector -2, 2. Okay. V is the vector 3, 4, -1. V is denoted using some dotted arrow, just because since its third coordinate is -1, V is actually below the XY plane. Okay, so that kind of grayish area, that's the XY plane. Okay, so for that reason it's drawn using a dotted arrow. And W is this yellow vector, so it's also a linear combination of U and V. So we can do the same thing. We can let right, A and B for the moment have value 1, so W is equal to 1, 6, 1. And we can let A and B run between -3 and 3 and try to see what we obtain. Right? Again, for each specific values, we'll get a vector that is a linear combination of U and V. Okay, I can start playing these like this. I'll start the other one. Okay, and right, so you can see that, yeah, W move around. Now it's under the XY plane. Eventually, I suppose it will come up. Right, so we can look at this, but it's a bit difficult to see exactly what we obtain by looking at all these linear combinations. Okay, so it looks like W is going kind of around the origin, but of course the difficulty here is that this is all happening in R3, and I'm projecting all this onto your computer's monitor, okay, which is two-dimensional. That's why it's hard to see what is going on. Actually, since W is a linear combination of U and V, so it's AU plus BV, it means that W is on the plane, the two-dimensional plane, going through the origin, 0, 0, 0, and with direction vectors U and V. Okay, so this vector W, as long as A and B, move from -3 to 3, the vector W is going to trace some area on that plane that has U and V as direction vectors. So actually, a better way maybe to see things in R3 is the following. So rather, I will go back to R2. Let's just pause this. Let's go back to this one here. Okay, and I will just, right, so I can start, have these play again. Okay, maybe I'll just bring my tablet a bit closer to you. So you have to imagine now that, if U and V are on my tablet, so if I place the tablet like this, imagine that the tablet is part of the plane with direction vectors U and V, okay? And it is sitting in R3 in some position, okay? And the vector W, well, it's is moving on that plane. So I can I try to bring it a bit closer. I'm not sure how well you will see. Well, of course, just behind me, you can see what's on my tablet. Okay, but the point that also I want you to, it's a bit easier to imagine in R3 if you're looking at just looking at me holding my tablet. Okay, so you imagine that this is part of a plane in R3 that has vector u and v. And the vector w, which is a linear combination of u and v, is always on my tablet. So it's always on that plane. Okay, and it moves, as you can see, just behind me. Okay, and maybe you can also see it on my tablet as I move it closer to you. Okay, so all right. So this way we can actually see better that even in R3, the span of two vectors that are not parallel and non-zero will be a two-dimensional plane. Okay, so so this is what I wanted to show to you today. Right, so we can only illustrate things in R2 and in R3. Okay, so this was an occasion to show you a little animation. But in linear algebra, we want to work in Rn for any n. Right, so when n is bigger than 3, then at least we've got algebra to help us understand things. Understand, for instance, what is the span of a set of vectors.